Count these bees by eye and you quickly hit a wall. Their movement is erratic, overlapping, and seemingly random, a physical representation of chaos. But even in this chaos, there are constraints. If you divide this swarm into groups of 4, 3 bees are left out. In groups of 3, 2 are left. And in groups of 2, there is a remainder of 1. Our natural impulse is to guess. We pick a number, test the division, and repeat. But this is incredibly slow. Every incorrect guess is wasted effort, and there is no guarantee you are getting any closer to the truth. Mathematicians take a different approach. They don't guess, they build systems to translate physical disorder into a set of predictable rules. We know one more thing: the total must be a multiple of 5. By focusing only on the numbers 5, 15, 25, 35, and 45, we move from infinite possibilities to a manageable set of data points. Solving complex problems is rarely about raw brainpower. It is about choosing a framework that exposes the order hidden beneath the surface. To solve the B puzzle, we use the division algorithm, A equals B times Q plus R. Here, A is our total, B is the size of the group, and R is that leftover remainder. By testing the first few multiples of 5 against our constraints, we see that 5, 15, and 25 fail the other division tests, but 35 satisfies every condition, leaving a remainder of 1, 2, and 3 when divided by 2, 3, and 4. This logic was first formally recorded in Euclid's Elements over 2,000 years ago. Algorithms like this allow us to translate a chaotic physical reality into precise, verifiable results. We can also look at numbers from the inside out, treating them like physical organisms built from smaller, foundational parts. The fundamental theorem of arithmetic dictates how these parts are assembled. It states that every composite number has a unique recipe of prime factors. Take the number 27,300. It breaks down into a specific string: 2 squared times 3 times 5 squared times 7 times 13. This is the number's DNA, a prime fingerprint that cannot belong to any other value. When you have the prime DNA for 2 different numbers, you can find their highest common factor by identifying which prime building blocks they both share. By comparing these strings, the largest common divisor becomes clear without the need for manual division. Mapping a number's DNA allows us to predict how it will interact with other values before we even start the math. This prime DNA even determines the fate of fractions. It is the reason some decimals end neatly, while others repeat forever. Look at 3/8. The denominator 8 is built entirely from 2's, guaranteeing the decimal terminates at exactly 0.375. But a denominator with any other prime, like 7, forces an infinite loop. The decimal repeats forever because its structure cannot divide evenly. DNA categorization allows us to know a number's destiny, whether it will be a clean result or an infinite cycle, just by looking at its prime components. As we move from small numbers to the massive scales of biology or astronomy, growth becomes exponential, quickly reaching sizes that are difficult to visualize. Logarithms act as a compressor for this complexity. They allow us to manage these massive scales by turning difficult multiplication into simple addition. The product rule shows how this works. The logarithm of a product is simply the sum of the individual logarithms. We are essentially working with the exponents, making the calculations much more manageable. This allows us to map the infinite reaches of the universe, using calculations that stay within our human grasp. We already use these kinds of systems in biology, grouping human teeth into incisors, canines, and molars to understand their different roles in our survival. Remainders, prime DNA, and logarithms are the functional categories of the numeric world. They are the systems of organization we use to make sense of the infinite. Mathematics provides the structure that allows us to classify a chaotic universe and use that organization to predict exactly what happens next.